Most programming languages have a function that, in theory, generates random numbers. For example, Java has the java.util.random class. Python has the random.py module. However, if you look closely at the documentation for these things, you'll see a lot of hedging going on. The problem here is that computers are the exact opposite of random. Everything they do is 100% predictable based on their programming. So, how can a computer generate random numbers? Well, ultimately it can't. What it can do is generate what are called pseudo-random numbers. So one commonly used approach to doing this is called the linear congruential method. And to do this, we need four things. We need a modulus, we need a multiplier that has to be between 2 and the modulus, an increment that has to be between 0 and the modulus, and a seed that also has to be between 0 and the modulus. Okay, so once we've got these values, we can generate a sequence of pseudo-random numbers between 0 and m. In other words, every value in the sequence is going to be between 0 and m. And just to be clear, possibly including 0, but not including m. Right? And the way we're going to do this is we're going to iteratively calculate the remainder of this linear expression when it's divided by m. In other words, we're going to look for the smallest possible positive value that is congruent to this linear expression modulo m. And the way we do that, you just look at the remainder, right? I'm going to take this number and I'm going to find the remainder when I divide it by m. That'll be the smallest possible positive number, again, right, positive only, that is congruent to that expression. All right, so let's actually do this. Now let's pick some numbers. I'm going to let m be 5, I'll let a be 2, and I'll let c and the seed both be 1. So the seed is actually our first value. So x sub 0, the first number in the sequence, is equal to the seed, which for our example is 1. So the next number in the sequence, x sub 1, is 2 times 1, the previous value, plus 1 mod 5. That's 3 mod 5. Whoops, sorry, I messed that up. 3 mod 5. And 3 divided by 5 has a remainder of 3. Now we do it again. X sub 2 is 2 times 3 plus 1 mod 5. That's 7 mod 5, and when you divide 7 by 5, the remainder is 2. And we keep going, right? X sub 3 is 2 times 2 plus 1 mod 5. That's 5 mod 5, and the remainder there is 0. And should end up with one more here. This is 2 times 0 plus 1 mod 5, which is 1 mod 5. The remainder there is 1. And notice what happened. Now we're back to where we started. Right? X sub 4 is equal to x sub 0. And at this point, the sequence starts to repeat. If I put 1 in there again, well, I'm going to get the same value I did the last time I did it. So x sub 5 will be 3, x sub 6 will be 2, and so on. Right? So we've got our sequence now of pseudo-random numbers. Let me write it out. Right? The first number was 1, then 3, then 2, then 0, and then they start to repeat. 1, 3, 2, 0 again, and so on. So this algorithm has some interesting properties. Right? First, it's efficient. It can be used to generate a large number of values in a very short period of time. Second, it's deterministic. The results are entirely predictable based on the formula, which is very helpful for testing purposes. And finally, the process is periodic. If done repeatedly, it will ultimately generate every value, well, not every value, it will generate a sequence of values between 0 and the modulus and then start repeating. If you look back at our last example, you'll see that it does not necessarily have to generate every value. 4 is between 0 and 5, but 4 never showed up in the sequence, so it doesn't necessarily have to include every value. Okay, so that deterministic thing, that may seem like a problem, right? Because we're looking for something that's random, and if it's deterministic, it's predictable, which is the exact opposite of random. Well, there are some things that can be done to minimize the impact of that predictability. All right, first, the values of the 4 parameters can be chosen to be really quite large, which creates a lot of possible outputs. So there's a lot of possible numbers you could get out, which makes it harder to predict what number is going to be next. And the results can be further obscured by choosing a different seed every time the program executes, right? So if you want a new number, you don't necessarily go back and take all 3 of the same values. Take your previous value as the new x and plug it into the formula, right? One way of doing this programmatically is to create a new seed value every time, and you let the seed be the number of seconds that have elapsed from a fixed date, right? Numbers generated this way aren't truly random, but the large number of possible outcomes combined with the difficulty of predicting what that seed is going to be make the results good enough that we call them pseudo-random. So we've got one more application we're going to discuss, right? In the next lecture, which will be the last one in this series, we're going to talk a little bit about applications of this idea of congruences to cryptography.